the first thing you do in finding this derivative is to go ahead and multiply it out, right? Because remember that like our power rule and things like that, they don't work when we have the two sets of parentheses multiplied by each other. I can't just take the derivative of one, take the derivative of the other, and call it good. So I got to multiply it out first, and then having done that, now I can actually worry about finding the derivative. Now pay attention to your notation. When you wrote this, it should have just been f of x, no prime. When we are now taking the derivative, that's where we're including the prime. Sometimes we get a little sloppy with that. That can lead to problems. Just be careful with it. All right, now we apply the power rule. And so for each of the terms, we use our power rule as normal, where we just take the original exponent, multiply it by the original coefficient, and then subtract 1 from that exponent. And we do that for every single term here. So this is our derivative. We're going to go ahead and call this good. We're going to call this done. That is our final answer. Now then, today, well, we are going to learn a new derivative rule. And so we're going to have to be able to deal with something that looks like this now. So taking a look at this one, there is some stuff we could do in terms of rewriting it, where we could go g of x equals e to the x times x to the power of 1/2. I mean, that's fairly typical of what we would do to find the square root derivative. But I still have e to the x times x to the 1/2. Can I combine those into a single x? Can I make that adjust into the x appearing once there instead of twice? Not really here. Because here the x is in the exponent, here the x is in the base. There's not a way to do that. So every rule that we have so far is unable to cope with this situation. But there is a rule that does allow us to deal with it. Because what's happening here is that we are actually multiplying those two values. So I can find the derivative of this, and I can find the derivative of this part of the function, no problem. It's just a matter of how do I find the derivative of the product. Because of course when I multiply I get a product, right? So we need the product rule, which will go onto your derivative rules page. Now the funny thing is about this one is that as you take a look at it, this just looks like a lot of tough stuff to follow, right? Sometimes that d over dx notation is easier. Sometimes it's not. We could actually shorthand this a little bit using the prime notation. Write it down either way or both ways, but at least write it down in the way that you're going to remember it. I'll tell you, I remember it the second way. All right, now a few little notes coming out of these notes. By the way, you'll see that this is indeed the same thing as we have written down there. So it's like f times the derivative of g, f times the derivative of g, g times derivative of x, and g times the derivative of f. All right. Now, as you take a look at it, and I'm going to use the second one as an example of this, just to kind of illustrate, does the order matter here? Like, what if I went to do the second one, and I'm like, well, I don't remember which one, so I'm just going to go ahead and do, like, f prime times g plus g prime times f. Would that work? Would that still give me the same answer? Yes. I changed the order that some of them were multiplied in, but that's okay, because order within multiplication doesn't matter. I changed the order that I added them in. That's okay, because order with addition doesn't matter. So with this particular formula, unlike some others we will see, the order in which you do them doesn't matter. The key thing is that when you are writing and finding your derivative over here, you're doing original times derivative plus derivative times original. That's really what you need to remember. So then, let's go back now to this problem that we were looking at before that we couldn't do, but now that we have the product rule, we can do it. And again, we'd start by just writing this as e to the x times x to the 1/2 power. But again, it is times x to the 1/2 power. That means it's a product, and therefore I can use the product rule. So let's go ahead and see how the product rule would apply here. So I'm going to find g prime of x. Now, in the original one, it talks about how we have f of x and g of x. That's not this g over here. The f of x and g of x in that formula are the two different functions that are being multiplied here. So it's the e to the x That's playing the role of f of x. And the x to the 1/2, that's playing the role of g of x, if you're looking back at your notes directly. All right, so then, I'm going to do original times derivative, so that's the original e to the x, times the derivative of x to the 1/2, which is 1/2 x to the power of negative 1/2. And then I need to add to that. So I just did original times derivative, so I now have to do derivative times original. So I'm going to do the derivative of e to the x, which is e to the x. Nice and easy, right? And then that's going to be multiplied by original, which is x to the 1/2. All right, that is actually the derivative now. We've done it. We've done product rule. Now, could we clean it up? Yes, we can go ahead and clean this up. So g prime of x, if we wanted to clean it up, there's a few different options that you could do. Some of you might be noticing that we can pull that e to the x out of both terms. So we could factor that out if we wanted to. You don't have to, but you can. And then the 1/2 x to the negative 1/2, that's 1 over 2 root x. And then I took the e to the x out of that second term, so I'm just left with the x to the 1/2, which is the square root of x. So I could write it like that. I could even try to go further and make it a single fraction and stuff like that, but all of these are things you can do but don't have to do. The actual derivative was that part. That just looks kind of messed up and scary with all the fractional exponents and stuff like that. So now, having seen product rule in action there, this is the sort of problem where we had to use product rule. But remember the very first problem that we found the derivative of today? If we had known product rule for that, we could have found the derivative of that using product rule as well. So let's see how we would do that. So this is the same problem that we saw at the start of class, but now I want you to be able to find this derivative using the product rule specifically. All right, now if we're going to do this using product rule, I'm going to be doing original times derivative plus derivative times original. So original first function, 9x to the 5th plus 7x. So that's original, and I need to multiply that by the derivative of the second function. So the derivative of 4x cubed is going to be 12x squared. And then the derivative of negative 5, it's a constant, and so that derivative is 0, so that's our first part. And then we add derivative times original. So I'm now going to be doing the derivative of the 9x to the 5th, which is 45x to the 4th plus 7. So that's derivative, and then that needs to be times original. So times the 4x cubed minus 5. And so we have our derivative. Now, this one doesn't look nearly as neat and tidy as what we found first, though, right? Is it going to actually equal the same thing? Well, let's find out by tidying it up. Let's go ahead and distribute this out just as a way to prove whether this does, in fact, give us the same answer or not. And so we go ahead and multiply it all out, combine them together. Did we get the same thing? Yes, we did. Now, you'll notice that now we actually have two different methods that we could use when faced with a problem that looks like this. You can either multiply it out first and then just use power rule, or you can go ahead and use product rule at the start. And then depending on the problem, you may or may not need to actually multiply it out. Because this technically was the derivative right here. Technically you could stop there, but a lot of times we do have to simplify our answers, and if we do need to simplify them, you'd have to go to here. So when you see this type of problem, which one do you use? Well, whichever one you prefer. It's up to you. So it's a matter of which one you think is easier for a particular problem, for a particular situation. So then another one that I want to take a look at here, because this is actually something I see happen a lot later, and I want us to see why it works the way it does, is I want to use product rule to find this derivative. And I know you're probably looking at it and thinking, we don't need product rule for that, we can just use power rule. But technically, when we use power rule, we're also using the constant multiple rule. And so what we're going to do here is we're going to see that if I treat this as 15 times x to the 4th, so there's my product, we're going to see why the constant multiple rule works the way it does. So go ahead and find this derivative using product rule. All right, so for finding this derivative using product rule, I'm going to do original times derivative. So the original in this case is the 15, and then I'm multiplying that by the derivative of just x to the 4th. So that's going to be 4x cubed. All right, then I need to add to that derivative times original. What is the derivative of 15? 0. And then that is multiplied by original, x to the 4th. And so then when I go to clean it up, notice 15 times 4x cubed gives me the 60x cubed. And then what's 0 times x to the 4th? 0. And so that's totally gone. And so notice the product rule, even if we do apply product rule to the situation when we don't really have to, it still works. That's really what the constant multiple rule that we have down to our notes is talking about. All it's doing is saying we don't have to use product rule when it's a constant because it's going to zero out that other term. This is also very important to see because we're going to be layering on more and more and more of these rules. And eventually, what happens is some people start thinking they need to use product rule with something that looks like this. You know, stuff starts getting mixed up and we try to make things more complicated than we need to. It happens. But first of all, I want you to see that you can use product rule if you really want to, but that the derivative of the 15 is going to give you 0. Where I see people run into trouble is they try to force product rule onto it. Okay, fine, you're doing more work than you have to, but it'll still work. But then they don't get 0 as the derivative of 15, and that causes problems. So I really want to show this explicitly so we can see that and start safeguarding our brains towards not making that error. All right, another problem where, strictly speaking, yeah, you're going to need something new today, right? And you notice for this problem that we do need to use product rule because we're mixing the exponential with the polynomial here. And so those are going to be our two functions that we're finding the derivatives of. All right, so we're going to do original times derivative. So the original of the first one is the 4x squared. Then we do times the derivative of e to the x. And of course the derivative of e to the x is e to the x. Then plus derivative times original. The derivative of 4x squared is 8x. And then times the original e to the x. All right, can we clean this up from here? Not really. I mean, maybe you could factor a 4x out of both terms. That'd be the most you could do, but that isn't even strictly required. We're okay even just leaving it here. All right, so having done that, I think we're getting the hang of it. So let's just do one last problem. Please find the derivative of this function. All right, so I looked at it as our product being of the x to the 5th and then the parentheses there. And so you can see that if we use product rule there, this is what we end up with. And of course, we could go ahead and expand it out as well. You don't, strictly speaking, have to. It's still the derivative either way. But was this the only way we could have gone about doing this derivative? No. Some of you might have actually chosen, instead of doing it that way, you might have actually started by distributing the x to the 5th into both terms. And if you had done that, then you would have started by writing f of x equals 4x to the 12th minus 3x to the 5th e to the x. Well, if you did this, this will still be okay. And the thing is, though, that we might have thought, well, by doing this, I can get around having to use product rule. And we can't quite actually get around it. Because when we do this part right in here, the derivative of that second term, we would need to use product rule for that part of it. Now, I want to show you, though, what would that look like. In fact, actually, before I show you, take a moment, write out, what do you think that derivative would look like for that second term? And if this is what you got, you're doing well with product rule, but there's a mistake here. Yeah, notice that we were supposed to be subtracting this, right? If I had done this, then that would be correct, because we're subtracting that derivative. And so I could say that way. Or alternatively, you might have jumped ahead and said, well, that makes that a minus there as well. Either way will be correct, but that's a very common error to run into. So just be very cognizant of that so that you don't run into that yourself. My suggestion would be start by putting the parentheses around it. But either way, it's going to work out. And yes, in case you're curious, if we expanded this out, yes, we would end up with the same thing.